Okay, so in yesterday's class we started looking at the or we finished looking at the impedance matching, and we kind of started looking, I think almost finished the technique to match to complex loads, right? And I think I asked you folks to try it out at home, maybe. So did any of you try out matching to some complex, some example? Maybe we didn't give any example. Okay, so please try it out as a homework, right? Maybe you can try matching 200, we did 200 to 50, right? Maybe you can try some 200 to 50, let's say 50 plus J20 ohms, something like that, as an exercise, right? And try out some of the examples to see which for you and whether you're able to check the Q or not. Okay, but are there any questions about 1 gigahertz? So the rest of things remain the same. If you are doing an L match, you can assume at 1 gigahertz you match from 200 to 50 plus J20. Okay, so maybe I'll write it down here. Okay, then you can try, I think we discussed the T match. Okay, since we have not done the T match example anyways. You can assume Q is 5. I think that's the example we did in class. You can try the same example. No problems. Okay. Any questions on impedance matching so far? Okay, good. So in today's class, we'll start looking at some systems concepts and eventually lead to the LNA. Okay. So I'm changing the material, the order of the material from previous years to help you folks get started as soon as possible on your projects. Okay. So so far we have seen that the possible receiver, I think we drew the the simplest possible transceiver, okay, looked something like this. So on the receiver side, let's start looking at the receiver side. You basically have an LNA, you have a mixer, and you have the baseband circuits. Okay, it could be some amplification, some filtering, some ADC, and so on. We are interested in the RF portion. And we discussed very quickly why we need a low noise amplifier, right? So first of all, why do we need a low noise amplifier? We said that the signal received is extremely small. Okay, so you need to amplify it while adding as little noise as possible. By definition, that's a low noise amplifier. Okay, so now we want to put down some very basic theory to this to figure out how do you figure out how much noise the LNA adds, right, such that your system still works, and so on. To do that, we need to understand noise analysis of a receiver. Okay, all of the analysis is extremely simple. Okay, but let's just do this. So first question, okay, so this is our prototype receiver. Okay, we will make it more, I guess, add the bells and whistles on, right? We will figure out whether you need to do it the receiver this way or something else, okay, some other way, and so on. There are several ways of building the receiver, but this is the simplest possible one. So what we said was followed by a mixer, and what we have studied so far, this is 50 ohms. We want this to be also 50 ohms. We want this impedance matching. Okay. So first question, okay, if I just want to check the noise, so this is Vs and Rs, okay, going into the LNA, I want to figure out how much of the noise from the resistor Rs, the antenna is passive, its electrical impedance is 50 ohms, and now how many of you are not doing the analog IC design course or have not done? Have you done it in the past? You're doing it now. Oh, okay. So, well, I think you'll have to catch up on circuit noise of the resistor, noise of the transistor, etc. Okay, you'll have to catch up on it. You can have a couple of classes worth of notes. But I think most of you know that a passive circuit produces, any passive resistive circuit produces noise, okay, based on the temperature at which it's operating. Okay, if you have a two-port network, okay, which is being driven by some Thevenin equivalent, Vs and Rs, R Thevenin, and it has some output impedance R out, this is passive. Okay, what do you think the noise will be across the output of the two port? What is the signal equivalent across the output port? What is the signal equivalent? It is the open circuit voltage in series with the R Thevenin, right? In this case, it's R out. So if you were to, so this is the open circuit voltage and this is R out. This is the equivalent of the circuits looking back at port 2, correct? You can show that if the network is passive, okay, the noise produced by this two port at port 2 equal to the noise produced by the Thevenin resistance. Does that make sense? You can prove that this is the signal equivalent. You can show that the noise equivalent one minute. The noise equivalent is just 4 kT RF delta out across port 2. Okay, any passive circuit will produce the same amount of noise as the Thevenin resistance. This is not true for active circuits. This is true for passive circuits. So for us, we are not interested in how the antenna is made. We know that it is passive. It presents an electrical of 50 ohms. Okay. Therefore, the noise equivalent will be 4 kT Rs delta F, a noise squared, voltage squared noise in series with Rs. Okay, so if you are analyzing the circuit for noise, you would replace the resistance Rs with its noise equivalent, which is the resistance in series with 4 kT Rs delta F. Okay, this is the squared, so I'll call this Vn Rs squared. Okay, now what is this going in? This circuit is going into the LNA, into whatever circuit. It could be an LNA, it could be the matching network, doesn't matter. In the end, I can replace the rest of the circuitry by the Thevenin input impedance, which is Rin, and hopefully if you have done a good job of matching, it should be equal to Rs. Make sense? So now I am interested in how much noise is going into the circuit. How do I find that out? Right? So I am producing some noise. I want to see how much of this noise is going into the receiver. R in stands for the receiver. So I want to know how much noise power is going into R in. How do I calculate that? Voltage will divide halfway. So this voltage will be Vn Rs by 2. Okay. So what is the noise power going into the good. So I'll call this noise power going into the receiver is simply Vn Rs by 2 the whole squared by Rs. Okay. This is basically 4 kprs delta F by, in fact, if you want to be accurate, by Rn, because Rn may not be exactly equal to Rs. So this is basically Kp delta F if Rn is equal to Rs. What does this mean? The antenna, it is producing broadband thermal noise equivalent to a 50 ohm resistance. You integrate that over a bandwidth B, you will get the total noise power going in. This is the power spectrum. So Kt is the power spectral density. Kt times B will be the power in watts going into the receiver. Okay. Can you please calculate at 300 Kelvin what the value of Kt would be? Kt. Okay. Can you calculate it in dBm per hertz? You know how to do that? Huh? 114, no. It's not 114. Yeah. dBm? dBm. But without bandwidth, you can't find out dBm. Over 1 megahertz. Okay. So, if I just want to find out Kt in dBm per hertz, what is it? 174 minus. Okay. So, this is why did you say 114? You had it before for something? In which course? Oh, the IoT course. So you have seen part of this before. Okay. The available noise power at the input is basically minus 174 dBm, that's the power spectral density, integrated over a bandwidth B, so plus 10 log B in watts. Okay. Now what decides this B? This B could actually be decided by many things. Okay. So the antenna itself may be frequency selective. Okay. You may have a very strong filter between the antenna and your receiver, in which case the noise, out of band noise, will be filtered out. Okay. So there are many different cases which will decide what the value of B is. If you don't have any filter, right, then maybe there is some filtering going on inside the receiver, in which case you would just consider the bandwidth of interest. Okay. But for now, this B, you will have to find some way to restrict B to only your bandwidth of interest. Because clearly, if you don't do this, you will get more noise going into the receiver. Right. So obviously, you should not be going into the receiver, you should not be seeing, you should not be considering a larger bandwidth than what you require. Okay. Let us say if you take wireless LAN, maybe it operates from 2.4 to 2.48, let us say, right, in the 2.4 gigahertz band. You don't want this receiver to operate, from 2 to 3, right? You'll be adding in noise from 2 to 3 then. You probably want to put in a strong selective filter right there. Make sense? Yes. Very good question. We are going to, when we decide what the right hand side circuit is. This is the noise of the antenna. So in some sense, this is the input noise floor, right? Side circuit noise will be configured as and when we figure out what that circuit is. Okay. In fact, we are going to do that next. Any other questions? Okay. So this is the input noise, total input noise. Okay. Floor, basically the part spectral density is clearly minus 174 dBm per hertz. Okay. Okay. Now, since, yes, how is it by hertz? So since it's the part spectral density, you just say it's by. In reality, it is not, right? So there is a logarithmic operation. So you just call it, since it's the part spectral density in dB. So if you took the part spectral density, it will be watts per hertz actually. Then you just consider it as dBm per hertz. That's all. Okay. The voltage across the resistor Rn is Vn by 2, right? So then the power is Vn by 2 the whole square, V squared by R is the power. This is not Vn Rs is the noise, it's the symbol. It is not Vn times Rs. Is that what you are asking? It's just V squared by R, that's all I have done. Maybe what else, I don't know what else to use instead of Vn Rs. Okay. Rs here is just a subscript. Okay. Now, since all of these are circuits are being used for communications purposes, what are you interested in at the end? You are interested in the signal to noise ratio somehow. So you need to figure out a way to characterize of these kinds of circuits, okay, based on signal to noise ratio. From the analog ICs course, you know that you characterize it based on input referred noise, right? If you take any analog circuit, you characterize it based on input referred noise, voltage and current, right? So if I take any 2 port, okay, I can characterize its noise by input referred noise source En and In. This is a general 2 port. Okay, but if you remember, all RF components are actually characterized based on 50 ohm impedance. It's not random, right? So if you consider each component as a discrete component, if you are building an LNA alone or a mixer alone or some filter alone, the input impedance and output impedance have to be 50 ohms unless it's on the integrated circuit. Okay, which means you can do slightly better. You don't have to stick to En and In type of characterization. You can, because there is a standard impedance, this impedance will never change. This En and In came up because you want to worry about both circuit with ideal voltage source, ideal current source, right, and some random impedance, V Thevenin in series with R Thevenin, right? Whereas here, you know that you are always going to use it only with 50 ohms, and more importantly, you are always going to be using it for some signal to noise ratio, power, signal power to noise power ratio. So for these kinds of RF systems, the noise is specifically characterized using a definition called noise factor or noise figure. Okay, I don't know if you covered that in the other IoT course, maybe you already have. Okay, so noise okay, so it is either characterized as the noise factor or the noise figure in dB, which is basically 10 log f. So what is this noise factor? So the noise factor is defined as follows. So I take the 2 port, assume that it's matched, right? Whenever you take an RF component, you have to assume that it's matched, okay? Okay. And also matched here. Okay, assume that input and output are matched to 50 ohms. So R out, RL, RIN, RS are all 50 ohms. Okay. In such a condition, this is a priori assumed to be true. Okay. In such a condition, you are going to define noise factor F as so you are going to define it as total noise at the output, okay, over noise at the output RS alone. So in other words, you are going to calculate, so inside this 2 port you might have various circuits, transistors, resistors, etc., each of which is going to add noise. If you were to find out the total noise at the output, okay, what all will that include? You do not consider the noise of RL for this, okay. So the noise, when you calculate this noise, it will include noise from RS, noise component, okay, inside the 2 port. Then you assume the 2 port is noiseless, it does not add any noise at all, okay. You consider the noise of RS alone and then find out what appears at the output. You take the ratio of these two, this will give you something called noise factor. But what does this really represent? What you are saying is it basically represents the additional noise, right, from the 2 port itself, because the numerator will contain noise due to RS at the output plus noise added by the 2 port at the output, okay. So if you were to write this N out due to RS, N out due to the 2 port, okay, by N out due to RS alone, okay. So this is basically 1 plus you will get a factor like this, okay. What does this mean? If you had an ideal noiseless 2 port, okay, what is the noise factor? It's 1. Noise figure is 0 dB. Okay, that gives you a baseline. Okay, if you have a noiseless 2 port, okay, your noise factor is 1 by definition, noise figure is 0 dB. Okay. Okay. Now it turns out that you can also represent this noise factor definition using SNR, because we started off with SNR. So it turns out, so imagine now along in series with this VNRS, you also had VS, which is the input source. Okay. Right? Now you can calculate the signal to noise ratio. Agree? It turns out, if you do this, if you go through this, you can very that actually what happens to the signal to noise ratio as you go through the 2 port? It degrades, because as you keep encountering noisy circuits, the signal noise ratio will keep degrading. It turns out that the noise factor is nothing but the ratio of the SNR at the input over the SNR at the output of the two port. Okay. The reason is, assume that the two port has a gain A. You can quickly show this. Just assume that the two port has some gain from input to output while under matched condition. Okay. The let us say loaded voltage gain of A, right? The output noise will just be Vn squared Rs times A squared. Correct? The output signal power will just be Vs squared times A squared. Correct? You can also find out the N out. Okay, it will just be Vn out, and then if you just take the ratio as defined previously, total noise at the output over output noise due to output alone, or take SNR in over SNR out, they will give you the exact same expression. You can quickly confirm for yourself for any random two port. Okay, so you can use either of these two definitions. If you have an ideal noiseless two port, the two port does not add any noise, input SNR should be equal to output SNR. Okay, noise factor is 1, noise figure is 0 dB. Make sense to everybody? Okay. Next question. I have done it for a two port, but now let us say I have a cascade of two ports. How do I find out the noise figure? The noises. Okay. Add the noise figures. Okay. So let us see if that will work for us. So this is 2 port 1, 2 port 2. Okay. This has F1, F2. Okay. I want to find, they are all matched, impedance match condition. I want to find out the overall F. Where will I start? So first, you have to realize two things. So first of all, you can start from very basic definition of noise factor, total output noise over output noise due to RS alone. Right? In this case, RS is here. You can start from this definition, right, and calculate it. But you have to realize one more thing. These noise factors F1 and F2 have been defined when the two port is driven by RS. Okay. So the way the noise factor is driven by two port is to say its input is matched to RS. I am now driving it with RS. Okay, its noise factor is so much. Okay. So the first thing you have to realize is that these two should also be matched. They better be matched. Okay. The intermediate impedance should also be 50 ohms, because if instead of choosing 50 ohms as your reference impedance for defining noise factor, if you had chosen 100 ohms or 75 ohms or something else, the value of noise factor will change. Okay. So if you calculate noise factor for 50 ohms, it will not be the same as noise factor for 100 ohms, 75 ohms, etc. So noise factor is always defined for a particular impedance. By definition, if nothing is said, it is 50 ohms. Okay, that's number one. The reason this becomes important for us, if you do integrated circuit design, the intermediate impedance is under your control. You won't have to stick to a standard of 50 ohms. So imagine you have an LNA and a mixer, right? The intermediate impedance need not be 50 ohms. You can choose to define it to be whatever you want inside the integrated circuit, because that is custom design. If you are now selling an LNA part and a mixer part separately, you have to match it to 50 ohms. Okay, in which case that is defined. So when you calculate noise factor for a cascade, you have to ensure that the intermediate impedance is 50 ohms also. Otherwise, you will indeed be in error when you calculate. Okay, that's the first thing to remember before you even start applying the definition. Okay, but assume that your everything is 50 ohms. How do you calculate from first principles? So first, you need to know the gains of these two. Okay, so let us say the gain is some G1 and G2. Can you please calculate the overall noise F? So now let us start from first principles. it is the overall output noise, total output noise. Okay. So what is the total output noise? The total output noise is going to have a component, of course, from V and RS. Okay. I'll call it A. I don't like to use G. G is used for a different parameter, which we'll come to. I'll call it A1 and A2 times A1 squared. Okay. Times A2 squared. This is the total noise due to RS. Plus, I need to find out the noise due to the first two port. What is that? The available noise at the output of the first two port, right, was Vn squared Rs times A1 squared plus out 1 squared. So let us say this had an output noise of Vn out 1 squared. I think that's what we had assumed. Is that what we assumed? I think we called it N out. Okay, assume that corresponds to some Vn out squared. And this has okay. Correct? The noise at the output of the first two port will get gain only by A2 squared to go to the output. Plus Vn out 2 squared, that will add directly over agree? What is this? This is simply 1 plus one squared by A1 squared sorry, Vn out 2 sorry, by Vn Rs squared, sorry, did I miss that? By Vn Rs squared. Okay. Now what is F1 itself? If you had to write down F1 in this form, what is it? Correct? If I just took the first two port alone, and because by definition that is F1. Agreed? What happens to the second two port? This is F1. What is F2? I would drive, say, the second two port with Rs alone. Okay, so I get Vn Rs squared times A2 squared plus Vn out 2 squared over A2 squared. Agreed? Okay. So F1 is 1 plus Vn squared by okay. This is just expression for F1 and F2. Yes? So F2, the way it is defined, I take the second two port, I drive it with a resistor. This has a gain of A2. So So this is RS. And I calculate the output noise. It's absolutely not. The cascaded noise figure is F. So that's why I said the individual noise figures are defined to be F1 and F2. Okay. The overall noise figure is F. We need to find that in terms of F1, F2, A1, A2, etc. Okay. That's what we are trying to do now. Okay. So now you please go back and what this is. What is the overall F? So this factor is nothing but F1 minus 1. What is this factor? F2 minus 1. Okay. So if you look at the overall noise factor, so this is F1. This is the way you calculate F2. So anyways, so F will end up being 1 plus F1 minus 1, F2 minus 1 by A1 squared. Now imagine I am going to generate, if you had a cascade of some n ports, n2 ports, right, you would basically get 1 plus F1 minus 1 plus F2 minus 1 by A squared. If you had a third 2 port which had a gain A3 and noise figure F3, you would basically get F3 minus 1 by A1 squared, A2 squared plus so on. So in general, so now I will just simplify this. F1 right, the noise of the n, contribution of the noise of the n2 port will be Fn minus 1, sorry, Fn minus 1 over A1 squared, A2 all the way to An minus 1 squared. Okay, what is this telling us? This is telling us bunch of things. First of all, the noise of the first 2 port is directly, the noise factor of the first 2 port is directly adding to the total noise factor. Okay, that is going to be the most significant component of your overall cascaded noise factor. The factor of the succeeding 2 ports are getting divided down by the total gain before that 2 port. Okay, so if you had a cascade of n stages, the nth 2 port has some noise factor that is getting gained down by the gain of A1 to An minus. Okay, in fact, this A1 squared, A2 squared, etc. are the power gains. It's a square of the voltage gain. Okay, they are normally represented as G, the power gain. Okay, so you might see an equation of this form. You might see something like this. Okay, this is called the power gain. Okay, under loaded condition, so the A that we have defined is the loaded voltage gain, matched at the input, matched at the output. That is not the same as the voltage gain of an amplifier that we have calculated in the analog circuits course, where we have assumed that the input impedance is infinity, it's not matched to 50 ohms, the output impedance may be something else and so on. Okay, here they are all matched. This is not the unloaded voltage gain, this is the loaded voltage gain. So the power gain is the square of the loaded. Okay, what I mean by loaded is that the impedances are matched to the available voltage at the on RL. Okay, any questions so far? Yes. So what I said was, if I am building, if I am going to buy an LNA from the market, I am going to buy a mixer from the market and I put them together, they will have an intermediate impedance of 50 ohms. If I am going to make something else, the intermediate impedance need not be 50. build both on an IC together. If you decide to use Friis equation as we have derived it assumes that all impedances are 50 ohms. Because we have assumed that the noise factors are defined with respect to 50 ohms. If not, right, you will have to modify it accordingly. You can still derive a Friis equation if the intermediate impedances were not 50 ohms, but you have to be careful because factor by definition is always defined only for 50 ohms. It is not defined for some other impedance. So you now calculate the noise factor at that intermediate impedance and then you will be able to use Friis equation. Does that make sense? That depends on the circuit. I can't tell you a priori which one is better. Why not? I can calculate the cascaded noise figure in both cases and find out whether going down an impedance or going up an impedance helps me at all. I can definitely do that, no? So what you need to do then, let us say a cascade of two amplifiers. Okay? You are trying to decide if the intermediate impedance should be 50 ohms, 100 ohms, 25 ohms, something. Right? What you should be doing is to design the second amplifier and the first amplifier. So you design the first amplifier to have an output impedance of 100 instead of 50. Find out the noise figure of that. Okay? The noise figure of that may be different from when you design it to be matched to 50 ohms. Right? Obviously it will, because the circuit itself now has to change. Same thing for the second amplifier also. Now you now need to find out the new noise factor at 100 ohms instead of 50 ohms. Find out the cascaded noise. Find out the total noise figure. Whether it's different. When you find out the cascaded noise figure, right, the assumption is it's now automatically brought to 50 ohms. Right? Because somehow you can see that you are referring this noise back to the input, comparing it to the antenna noise floor. Effectively, because you are saying it's SNR in over SNR out, you are now, imagine you are now referring the noise of all your circuits somehow back to the input as an increase in the noise floor. So in fact, this noise factor F or noise figure in dB is going to lead to an increase in the effective noise floor because their SNR is being degraded. Okay? Yes? Again, I will have to be careful. If you are designing all of them on an integrated circuit, they need not all be matched to 50. In general, they will not be. To receivers. Here we are discussing only receivers. Okay. Because you can calculate the total noise figure F, cascaded noise figure. Again, what I said was that even if the intermediate impedance is different, no. Friis equation in this form assumes that everything is 50 ohms. Factors F1, F2, F3, etc. are all defined for 50 ohms and the intermediate impedances are all 50 ohms. Friis equation. So this is called Friis equation. This is defined for 50 ohms as it is, as we have derived it. Okay? Because assume that F1, F2, F3 are all defined for 50 ohms. Because we took each two port in turn, drove it with RS and found out the noise factor. That is the way we have defined it right from scratch. Okay? If your intermediate impedance is not 50 ohms, this will give you the wrong noise figure or noise factor value. Okay? Of course, this can be modified now, okay, to figure out what the new noise factor, cascaded noise factor should be if the intermediate impedance is not 50 ohms, because now you will need to find out the intermediate impedance for each block, calculate the noise factor for that intermediate impedance, okay, then write down the expression for total output noise divided by noise due to RS alone, and then you can calculate and you can find out a new Friis equation. Okay, that can be your equation for your transmitter. Unfortunately, you cannot give a common name because intermediate impedance is going to be different for each design. Okay. Any other questions? Yeah. That will depend on your circuit design. When you design each LNA or each mixer or the cascade of the two, you will find that some of them are better for noise, some of them are better for gain, some of them are, see, for a given power consumption, okay, if you reduce your output impedance, the chances are very good that the voltage gain will change. Now imagine that this is an amplifier, okay, port 1 is an amplifier, port 2 is another amplifier. If the intermediate impedance was not 50 ohms but 25 ohms, chances are very good that your gain is going to be lower because you now have to drive a lower load impedance. Your output impedance also needs to be lower. For a given power consumption, chances are very good that your gain will be lower. But chances are good that your noise may also be lower. Okay? Same thing for your next port 2. Now you need to match the input of port 2 to 25 ohms instead of 50 ohms. Okay? So its noise characteristics, its gain characteristics will also change. As you can see, the overall cascaded noise figure depends not only on noise factors F1 and F2, it also depends on G1, G2. Before you design this, you cannot say which one will be better. However, if I tell you, I can pose a question for you, okay? I have two amplifiers, G1, G2, F1, F2. Okay, I can connect them in this way. I can cascade them in this way. Let's assume they're all matched to 50 ohms. Which one is better? It depends. Okay, the two noise factors are different. If I choose some values, one of them will be better. Okay, if I choose other values, it doesn't depend only on G1, G2, it depends on F1, F2 also. It depends on a combination of the two. You can the two noise factors and figure out which is lower and go ahead. And that's what I meant when I say that you cannot say, one is better, lower impedance or higher impedance is better. It's a, case by case situation. Nobody can say. Yes. Why do the intermediate impedance need to be matched? Good, very good question. If I have a discrete receiver that I am building, chances are very good that I am going to get two separate components, put them on a printed circuit board with some distance between them. Okay, so let us say you are operating at a couple of 2-3 gigahertz. The wavelength on the board may be like a few centimeters, 6-7 centimeters. Okay, the board depends on the mu r and epsilon r of the material used for the board. Okay, it could be of several centimeters, 6-7 centimeters. The components themselves may be as large as a centimeter wide. You may need a 1 centimeter between them to make sure you can reliably solder them and connect them together. Okay, what that means is the distance between the two components is about approximately 1/5 of a wavelength or 1/6 of the wavelength. At that point, you have to consider transmission line effects. I think the typical rule of thumb is 1/10, more than 1/10 of the wavelength. Okay, if the dimension, physical distance is more than 1/10 of a wavelength, you have to consider distributed effects. But in reality, they start affecting you much earlier. Even 1/20th or 1/30th, they'll start affecting you. You'll see inaccuracies in your simulation. Okay. If you build it on an integrated circuit, you can place them much closer to each other. Now it depends on how close you can place them versus the frequency of operation. Okay. If you can place them, let us say 100 microns away or 50 microns away, operating at 2-3 gigahertz, that's very small enough such that you need not consider the effect. If you are operating at 30 gigahertz, you will have to consider the transmission line effects. You will have to consider reflections, you will have to make sure their impedance matched. And as you will see going forward, the simplest possible thing we will assume is that they need not be matched. Impedances need not be matched because they are so close apart. And that is what we will have the majority of our calculations for in this course. Okay? If the dimensions are close by, you need not match them. Okay, you need not match them. What really matters is the available voltage, because many of the circuits that we are building in will be common source circuits or common gate circuits, for example, where the input voltage signal is applied across the gate source of a transistor. Okay, if such is the case, you are only interested in the absolute voltage for many of MOSFET circuits. If you have the distributed effect, then you will have a standing wave. Much of the voltage may be reflected back. The actual voltage may be very. But if they are very close by, you can directly assume that they are cascaded. You are not interested in matching. In which case, your Friis equation will change. You may not even be able to apply Friis equation directly because you may not calculate noise factor. You may go back to the calculation that you assume in the analog ICs course. You can directly assume an input referred voltage divided by the gain of the preceding circuit and take it as an input referred noise. Okay, we will tackle these as and when we come. When we finish the LNA, we will automatically assume what the mixer input looks like and then find out. Right? In the next few classes, we'll see this. Okay. Any other questions? If not, we'll stop here. Do we have a class tomorrow? Normally Thursday morning first hour we have, right? Or Friday morning first hour. Tomorrow there is no RFIC class. Is that right? Just 1 minute, sorry. Oh, we do have. So tomorrow morning we will meet. Okay. Friday we will not meet this week.